Okay, we're going to talk about what you can do once you know how to find the doubling time of a graph. If you do, you can take the graph of the basic exponential function and relabel it. Okay, so to represent the function that you have, and then you can make estimates based on that graph. If you've got a good graph, you can make good estimates, then maybe verify those estimates. Let's see how the process could work out. Okay, so you got y equals p of t equals 500 times 1.05 to the t. Doubling time. Okay, then p of t sub d equals 2 times p of 0. As your time goes from 0 to t sub d, this p of t function will double. So, well, p of t sub d, you plug in t sub d for t, you get 500 times 1.05 to the t sub d equals 2 times p of 0, 500 times 1.05 to the 0. Okay, well, this says that 500 times 1.05 to the t sub d equals 2 times 500, because 1.05 to the 0 is 1. Divide both sides by 500, you get 1.05 to the t sub d equals 2, so that t sub d equals log base 1.05 of 2, which is approximately equal to 36. Now you can calculate that, use your calculator, log of 2 over log of 1.05, you'll find that it's pretty close to 36. So I'm going to just kind of round it off to 36. And I actually didn't do a sophisticated estimate. The rule of 72 works pretty well for a 5% interest rate, for example. Okay, so now we've got it. What can we do? Well, we can relabel. Okay, notice that the basic exponential function, and certainly you've seen this property, doubles every time your argument changes by 1. So if this is x goes from 0 to 1, the value of the function goes from 1 to 2, it doubles. If x goes from 1 to 2, the value of the function goes from 2 to 4, it doubles. If x equals -2, the value of the function is 1/4. If x goes to -1, the value becomes 1/2, which is, again, a double. Every time x changes by 1, the y value doubles. And that works for any numbers, not just the whole numbers. And you can verify that, and it's worth verifying. Okay? Well, that means that if you relabel this graph, so of course you got 0 here, and 36 here, and 72 here, that the value of the function is going to double every time x changes by, or t changes. Say this is your t-axis now, these are your values of t. Every time t changes by 36, your y value is going to have to double. And of course you can have -36 here and -72 here if you want it. A lot of times you're just interested in what happens for positive values of t, but sometimes negative values of t are important too. Like maybe you want to know what happened, what this value was 36 years ago, okay, or 72 years ago. Okay, well, all that's important. But see, we just relabeled this graph so that every time t changes by 36, the value doubles. Now the values of this function are different than the values of the basic exponential function. We take care of that by just saying, okay, well, I don't want that to be 1 anymore, I want that to be 500. Because, of course, when t equals 0, this function has a value of 500. Okay? So if 1 unit is 500, then we make this 1,000, and we make this 1,500, and we make this 2,000. And now our graph, I'll go ahead and make it yellow. It's exactly the same curve, but according to this labeling, the graph represents this function now. So we have the yellow function, y equals p of t equals 500 times 1.05 to the t. Now, we can make estimates, okay? So let's say we want to estimate P of 50, okay? Well, fairly easy to do. T equals 50. Well, let's see, halfway between 36 and 72 is 48. Add those, you get 96, divide that by 2, you get 48. Or you see there's 24 between here and here, so you add 12 to this. What? 36, you add 18 to this. And did I say 50? 48? I said 48. I'm making a lot of mistakes today. It's 54. Because you add 36 and 72, you don't get 96. You get 108. And you divide that by 2, you get 54. So let's see. That means 54 would go about here. So there's 54. And where's 50? Well, if I divide between 36 and 54, divide that in half, I see that 48 goes about here. And 50 is closer to, did I get that right? That's not, 45 goes about here. Got 48 in my head. Okay, and 50 goes almost halfway between 45 and 54, but a little closer to 54. So I'm going to put 50 right here. So I'm going to say, okay, that's t equals 50, and t then equals 50 everywhere on the vertical line. Okay, reasonably straight, but, okay, and then I make a horizontal projection. I'm really kind of trying here. That's not too bad, okay? That sure looks pretty much halfway, maybe a little more than halfway. Halfway between 1,000 and 1,500 would be 1,250. I think it's a little more than that. I'm going to say it's 1,270. There's my estimate, okay? So my estimate is P of 50 equals 1,270. Okay, well, I can check that estimate. I can plug 50 in here for T and see what I get. Now, I'm not going to attempt to estimate that. I tend to get something, the more I look at it, the more I look, that looks like it's kind of going downhill. So maybe 1,300 would have been a better estimate, but I'll leave that to you. Draw your own, make your own estimate, and then plug it into your calculator and see how close you got. Okay? So, or we could estimate the solution of the equation P of t equals 1,700. Okay? And of course, we could write out that equation in the form that you would want to write it to manipulate, but we want to use the P of t notation and understand what that notation is saying. So I'm going to write it that way, but okay, you got 500 times 1.05 to the t equals 700. Now that's an easy equation to solve. People did quite well in the midterm solving exponential and logarithmic equations. Okay, so I'm going to make my estimate here, and I'm going to say, okay, 1,700. Now, halfway between 1,500 and 2,000 is 1,750, so 1,700 will go just a little bit below halfway. Don't know if I really got that right, but let's just now project over here and project down. Okay, I arrive here. Now again, I can be subdividing this interval. Halfway between 54 and 72 is 63. So, 63 would go a little hard to see about here. So I'm going to estimate maybe that's 65. So our estimate is T equals 65, and then you can check that with a calculator. Give you a little better picture and a visual representation of how this exponential function changes.